Hello, welcome to this demonstration of the GWeasy software. Let's take a look at the different functions and the features available in the software and go through each one of them to understand what they do. To begin with, there are a couple of tabs as you can see, and each one of them performs one of the specific tasks of the gravitational wave data analysis. Uh, and to begin with, we have the web browser here, and it's an interactive browser that you can look through. By default, it opens up the GWS website, so you can take a look at the different data available, take a look at their documentation. So say for example I want to take a look at one of the latest data runs, that is the O3 run. I can look at the different naming schemes for the different channels and take a look at the data time availability and stuff like that. Moving on to the next tab, we have the graph fetch tab, and this one is focused on downloading the GWF files, the raw data, time series data from the interferometers through the NDS servers, and you can try to fetch the data using CSV files. So say for example you want to fetch the data for uh, two time segments that are as in here, so you can just enter them into a CSV file and then load it on here. Next you can select the different channels over which you want this time series data. So for me, for testing, I have selected these two channels that are from the 4000 Hertz sampling rate from the O3 run, and these are the auxiliary channels. Those are the ones that store the data apart from the main strength channel, taking a measurement of all the different uh, environmental parameters apart from the main strength channel. So stuff like the air pressure, humidity, electrical discharge, stuff like that. There are magnetometers, there's parameters, and there's also the sensors inside and outside of the interferometers to make sure that no external noise affects, or at least we are aware of the external noise that is affecting the data that we get. Anyways, moving on to the next tab, that is selecting the folder where you want to store the raw data files. So for me, I'll select folder name test GWF, and I'll store the gravitational wave files there. Once that is done, I'll hit on start execution, and it is while it is running in the background, let me move on to the next tab, that is the Omicron tab. Omicron is a statistical inference pipeline that was created to identify some regions of noise in the data from the LIGO interferometers. Of course, how it works is it identifies regions of time where some certain parameters that, as you can see here, are met, and so over them we can approximate like the regions of high noise, regions of low noise, and then also potentially categorize the parts of the data run into like category 1 to 3 based on the amount of noise that is present. So for example, let's put down some default values for identifying the noise in the signal, and let me choose the different values for these parameters. Say for example, I'll choose the SNR threshold to be 5.0 and the PST length to be 300. Now the primary way to store this time segments is through triggers, what is known as Omicron triggers, and there's also an option to create an HTML file that lists down these triggers just for easy accessibility and making a summarization of the entire Omicron run. You can select the output format to be either root or HDF5. I have selected HDF5 as it's more easier to convert it to CSV. You can also select the sampling frequency based on what you want. You can also type in some custom frequency if you want to. Moving on to the custom segs. Generally, what happens in when you work with Omicron is that you have to create an FFL file, but what this GWeasy software does is it creates an FFL file for you. An FFL file is simply a fancy way of providing Omicron with the path location of your GWF files. So, say for example, I had previously loaded the GWF files in this directory for testing. So it's the same channel that we had chosen. So let's choose this channel as our root directory, and as you can see, we have the two different time segments on our list. Of course, as you add more time segments, you can get a longer list and then select like which are time segments you want to run Omicron over. For me, I selected both of them, and then I'll press on confirm. So what this process did is it created an FFL file for me, and now I simply have to press on save config, which created an config file that basically tells Omicron what parameters to look for. Now I'll start the Omicron process. I'll take a note of the Omicron parameters here. Uh, that is the time range through which Omicron is running, which is useful in the next step. So here we are trying to plot the Omicron data, and what I'll do is I'll simply select the output, which I had also run over earlier, because Omicron is a little bit extensive when it is running. So say for example we choose the same channel, and once I've done that, the channel name is selected here, so you don't have to input it. uh, you can feed into the time segments that you want to run over the Omicron, and you can also select an output directory where you want to save the output images from these plots. Uh, so once that is done, I will click on run Omicron plot, and you have the different diagrams for which the Omicron triggers are present. So the colored elements here that you can see are the different Omicron triggers over the time segments that we selected. So as you can see, the color, or the third axis, is the SNR value based on the intensity of the color, and on the y-axis we have the SNR value versus on the x-axis we have the time segments, and in the different graphs there's different um, labels that you get. So one of them has like the rate, the sampling rate, one of them has the frequency, one of them has number of clusters. So it's a very good example of how the Omicron triggers work. Let me show up one of the plots in an image file. So as you can see, it creates the title of the plot and the timestamp along with the images. Um, moving on to the next step, we have the time series operations. So from here on, we are shifting our focus from running the Omicron to working on the main channel. Omicron is typically used to analyze over the auxiliary channels, whereas uh, all of the other tabs are focused on working on the main strain channel of the interferometers. So say for example you want to simply plot a waveform diagram of the time series data. Let me select like the catalog 2.1 confident, any of the events within that, uh, and I can also input like specific time range if I want. By default the start time is the start time of the event. I'll keep it short, so say for example a sample of 5 seconds, and I can select the different interferometers I want to use. So let me choose Livingston and Hanford to run the waveform over, and what it will do is it will fetch the data from the server, and it will plot the waveform diagram that is a simple strain versus time diagram of the interferometers during that time. And as you can see here, there are two different waveforms during this event. One, the red one is from the Hanford Observatory, and the blue one is from the Livingston Observatory. And if you are aware about the time delay between both, you can see there's a slight time delay between the two interferometers, as they are of course separate from each other's by a couple hundred miles. uh, there are some other features, like you can fetch the event URLs per event. More importantly, you can convert the GPS time to UTC time. So say for example, if you want to understand like what time in readable format it was during this event, then you can simply press convert and it will give you the time that was on. So this event was on 2019 April 12th of April at 5:30 a.m. And you can also do like an inverse of UTC to GPS if you want. Moving on to the next step, we have the fast Fourier transform. So pretty much the same steps for loading up the data. We'll choose similarly a 5-second window for which we want the Fourier transform, and we can choose like both of the interferometers. And once that is done, I can start the FFT. There's also an option to save the parameters if you want. What it does, it loads up this parameter into a CSV file that you can use for easily later on. As you can see, the event was run over and fast Fourier transform, and what it does, it converts the time segment data to the frequency domain, and it is more efficient because now there's more data crunched into a small amount of space, and you can get more meaningful information, as oftentimes noise is hidden in the frequency domain and not very easily visible in the time domain. And the last tab is the power spectral density, and let me load up similar parameters for this one and select maybe the same event just to get a better visualization. I can select a similar kind of 7-second window or 5-second window, and let me choose all three of the interferometers. For this one, you can choose the FFT length and the method, of which there are two, median and wedge, based on your requirement of the analysis. And similarly, this would fetch the data from the servers and plot down the power spectral densities in this time range. This is especially useful to understand like where in the interferometer during this time range there was a very high intensity of either noise or signal, but based on like the overlay of all three of them, right? For example, while there's a very high peak in the Virgo detector here, it's only a single one, so there's high chances that it is noise, whereas this event seems to have an overlapping of both Hanford and Livingston, so there are more chances that it is somewhere near a true event. So yeah, this is the power spectral density graph. Of course, you can save all of the plots as an image file wherever you want, and yeah, that is pretty much the entire run of GWeasy so far. Uh, there are more features to come. There's spectrogram dataset representation, which converts the time series to a spectrogram, and so similarly more and more tabs would be added, but it's a the GWeasy interface. It's a very no code solution. It's a very user friendly solution that is aimed to improve the user experience for people who are not very aware about coding or are not much into learning about different pipelines and the software installations and all of that stuff. So I hope that this demonstration provided you an easy walkthrough of the different software. You can follow with this video. There would be multiple videos about each of these functions and the details about how to work with different features. So if you have any doubt, please look through those.